Okay, good afternoon, good morning, good evening, everyone. Friends of IEEE out there in the IEEE Solid State Circuit Society EDS South Brazil Joint Chapter. We are on this channel, and I thank you very much. I thank you very much for being here in this channel to listen to Professor José Silva Martinez, who is the distinguished speaker of today's talk. And let me introduce Professor Silva Martinez. He received his PhD degree from Catholic University of Leuven in Belgium in '92. He's an IEEE fellow and holder of the Texas Instrument Chair professorship at Texas A&M University. And after PhD from '93 to '98, he was a researcher at the INAUE Institute in Puebla, Mexico, a research institute. He was the head of the electronics research department there for 2 years. Then he moved to Texas A&M, where he has been for the last 22 years. Professor Martinez's current research interests include the design and fabrication of integrated circuits for wireless communications, radar, power management, energy harvesting, and biomedical applications. Professor Silva Martinez has co-authored hundreds of papers, over 135 journal papers, 185 conference papers. He authored 3 books, holds 6 granted patents, 6 more pending. And he has served at IEEE in many, many roles, and we are very grateful that he has been such an active person in IEEE. He's technical chair of the upcoming ISCAS 2022, and as a member of the IEEE Fellows Committee for the last 2 years. He was an associate editor for IEEE TCAS 1 and TCAS 2 transactions several times. He serves currently on the board of the editors for other 3 major journals, so he has had many, many roles in our field. He was serving as a member of the CAS board for 2 years, a member of the Distinguished Lecture Program, senior editorial member of the JetCAS journal and emerging topics on circuits and systems. He has received many awards. It's too long of a list to mention, and I want to list all of them. He was an outstanding professor award recipient from Texas A&M in electrical and computer engineering department in 2005. So he's a very known person in our field, and we are very pleased. And thank you very much, Professor Silva Martinez, for agreeing to come to this channel and deliver this distinguished talk, the design of operational amplifiers for advanced ADCs converters. Everyone will be able to ask questions here by typing in the YouTube channel. So thanks for being with us today. We're very pleased and looking forward to hearing you, Professor Silva Martinez. The floor is yours now for talking to the IEEE audience. Thank you very much.
Thank you very much, Sergio. It's a real pleasure to be in contact with people from Latin America. Actually, I was invited as a member, part of the Distinguished Lecture Program. I was planning to visit a long time back in 2015, Brazil, several universities, including Rio Grande and Federal University of Rio de Janeiro, and also Santa Catarina. You know what? I went to Brazil. I got sick on Sunday. I was in the hospital one day, and I had to return back almost immediately. And I got a surgery almost 1 hour after I left the plane in Houston. Okay, that was again a very bad luck. And then, but I was always waiting for this opportunity. I hope I can visit you in person in the near future. Going to the presentation. This is a very old topic. I mean, operational amplifiers is something that was invented back in the 60s of last century. Still people is talking about operational amplifiers, and the obvious question, and this is something my students are always asking, is why we're still in this topic. Well, the main reason is because new challenges are coming with the new standards, and also the new technologies. The companies and the users are demanding more and more performance from the different systems, and then new challenges are appearing in this area. going to cover fundamental three topics here. After a background, I will discuss a little bit the challenges on pipeline ADCs. Then also the other important ADC area is Sigmadelta modulators, the conditions and the requirements for the amplifier for both popular ADCs are different. We will learn why. One is fundamentally capacitive, the other one is resistive loaded, and this makes a big difference when you are designing this kind of systems. What are the open areas and why you are still researching in this area? That's something I hope I can answer at the end of this presentation. And I will make some quick conclusions. Together with some recommendations if you want to do research in this area, what is from my point of view, the open areas that are looking for a solution. We know that our IC designs, especially analog-to-digital converters, they find applications everywhere. In any area, we always need to convert information from analog to digital and vice versa, digital to analog. In this particular talk, will be more focused on mobile devices and the requirements for and challenges for the emerging applications. In this chart, I try to show you what is the tendency of the technology, starting from 1G back in the middle of the 80s, till 5G, which is what we have now, and then looking into 6G and the 5G NR, which are NR stands for the new radio systems that are demanding more and more bandwidth. I will go back to this particular topic to see what is the technology that companies and research groups are embarked in. The main idea is just to have much more information in less time, and then you need probably more bandwidth. You need to also use more demanding coding schemes, and those are more sensitive to errors, and you need a better resolution in your ADCs. Okay. This graph over here looks like we are saturating the applications, but in fact we have to consider this scale over here. The rate is fundamentally low scale. You plot this one in linear. Probably you will see that this part is even a little bit kind of quadratic. Same thing happened with wireless communications. Wireline applications is more or less the same tendency. Bluetooth, in this graph, we have listed only AC standard, but AX standard is coming. And now this standard demands much more bandwidth, something like 160 megahertz of effective signal bandwidth, effective conversion rate, and that will require more demanding amplifiers. If we see the market, why this tendency and why we are moving in that direction? Well, this is more or less how the market, how the demand for smartphones is. Right now, it's something close to 3.5 billion smartphones. That's the market we are talking about. But mobile devices, connected devices, if you measure this one in billions, we are somewhere here. This is almost 10 times more connected devices than the number of smartphones. The number of smartphones is in the range of 3 billion. So this is 30 billion the number of connected devices. The tendency of the technology of the demand is increasing exponentially. Part of this demand is fundamentally a lot of IoT's application and connecting almost everything through wireless systems, and then connecting almost everything. That's the demand that we see over here in future, and those devices will require also some more demanding conversion rate. As an example, and this is probably an old information, it's actual, but if we are looking in future, probably I should change this number from 60 megahertz bandwidth to 400 megahertz, which is the new standard for new radios. In the past, we used to have only one channel per system, and the bandwidth was something like a 10, 20 megahertz. So a lot of ADCs in that area you check the journals and you check ISSCC and etc., all important conferences, you will see that a lot of optimization was done in systems with a 20 megahertz bandwidth. Now with the idea of carrier aggregation, now we can. The idea is to aggregate here 5 channels in the same system. Now the bandwidth is going to increase from the actual one is something around 100 megahertz. You can find this device already. Qualcomm is pushing in this direction, but the tendency is just to put up to 5 channels together, and then the signal bandwidth is going to be something in the range of 160 megahertz. For that reason, you see a lot of ADCs trying to achieve bandwidth of 200 megahertz or so, or a little bit more, if possible, with a relatively modest power. Now this is kind of the fashion in ADCs. 100 or higher megahertz with a 10, 11, even 12 bits resolution. Of course, the idea is that if you put more channels here at the input, now you increase the power at the input. You increase the power at the input, now those guys must be more linear, because now you have a more signal. And then you require better resolution in the entire system, like 11 bits or even more. This is continuously seen in the standards and in publications, especially from industry. Of course, the entire system must be able to tolerate the presence of blockers, since this is a broadband system. And in general, you need a high dynamic range in your system. Of course, many of those devices are for mobile devices, and power consumption is a major issue in this. And then the system, and a lot of companies are doing a lot of research on power management. This is another area that is very hot in different companies. At least in my group, I always get requests from companies asking for people with good skills on power management. And power management means buck converters, boost converters, linear regulators, battery chargers, etc., wireless chargers, a lot of this stuff, and how to optimize for power. That is, those are the topics that are quite relevant. But in this particular talk, we are interested in the ADCs. The chart originally was reported by Analog Devices, where they put here the resolution, effective number of bits needed for different applications, and this is the bandwidth required for all those applications. Radar and the emerging Bluetooth standards. AX is here, which requires something like 160 megahertz and maybe even in the range of 10, 11 bits resolution. Radar and some other applications are demanding bandwidths in the range of gigahertz and between 10 and 12 effective number of bits. But if we put on top of this one, 5 years old, 5G, 6G, this is just my prediction, it's going to be more or less in this range, okay? Bandwidths ranging 400, 500 megahertz up to several gigahertz, and with a very decent resolution. And this is really an issue. Pipeline ADCs and some other applications, even SAR ADCs, could probably satisfy those specs, but the question is if they can satisfy the specs of the effective number of bits. And a lot of research on calibration is done for these particular applications. You see what is reported in recent years in ISSCC and BLS side. It's nice that Boris Morman is making a very nice service to the community, having this chart where he just collected data from those 2 conferences. You see this is more or less the kind of limits or bounds for this for ADCs. The new application, the target is just to beat this kind of boundary over here. For modest frequencies, of course, you can achieve high resolution, but when you start just moving to higher bandwidth, now the resolution starts just dropping. And the dots in red over here are fundamentally contributions from different companies. One of them is from Broadcom, the other, all of them are analog devices, and some other companies, Xilinx is also present right here. And this ADC is an ADC that we reported last year. This is from our group. This tells you more or less, or put you in good context of what should be the target if you want to have a competitive solution in terms of a signal-to-noise distortion ratio and also bandwidth. But this is not the entire thing. In order to have a better picture of these challenges, you need to have power. Power, especially for mobile devices, is an important factor here. And then there's a figure of merit being proposed by Analog Devices, Richard Schreier in particular. What you know, if you really want to compare overall performance of your system, you really need to consider the signal-to-noise distortion ratio. You need to consider the bandwidth. It's not the same design in an ADC for 10 megahertz than for 100 megahertz or so. And you need to normalize this by the amount of power that you are using for this particular device. Unfortunately, in this figure of merit, we don't have a technology, because technology makes a big difference in this. But anyway, this is a good figure of merit that gives us an idea on performance, how good is your system. Now you see some of the red spots that I showed you before. Some of them are very power hungry, and for that reason, the overall figure of merit is not necessarily the best. And this is one of the actual problems right now. I think to complement this one, probably we should plot here power consumption versus frequency, or a 3D would be much better. A 3D plot with frequency, with power and bandwidth. I'm sorry, not bandwidth, SNDR. That will give us a much better picture on this the challenges. But really is a challenge to have a good performance and at the same time have a good SNDR and a decent bandwidth in this range. That's the real challenge. Okay, now why we cannot achieve those specifications? Why this is so difficult? Well, let me just be focused on this particular seminar on two particular cases, pipeline ADCs, and let's see in particular what the amplifiers, the problem with the amplifiers. For pipeline ADC, fundamentally is so-called Nyquist ADC, where the conversion from analog to digital has three steps. If we split this one, the first one is the sampling. We have a continuous time signal here, and then the first operation that we do mathematically is just sampling this information, which is nothing else than the multiplication of the input signal by a train of impulses that have a constant period. And then we fundamentally take samples of the input signal. Okay? Sampling, if you check your fundamentals on math, sampling is not going to introduce distortion, but it's going to introduce alias. Alias means repetition of your original spectrum around the frequency of the train of impulses. In reality, there is no distortion here, provided that you satisfy the Nyquist criteria. That means the alias of the replicas of the information are not falling in band, or part of that information is falling in band. If you satisfy this, you are fine. You don't introduce distortion, and then the number of levels that you have in this sampling is again analog, and this is number of levels is infinity. You cannot process this information with digital. You need to have a kind of a trade-off between how complex is the representation of the signal, how many bits I'm going to use for the representation of this analog signal, versus the complexity of my system. And then this is where we do a matching, a mapping of this information, and then we assign every single sample over here to the closest level that we define here, and then we define a certain number of levels right here, and then we do this matching over here. Now we are not going to make all the representation over here, but we'll have just a finite number of representations right here. And this is where we introduce distortion. I mean, this signal over here, which is quantized, is not exactly equal to this because we introduce errors. For instance, this sample over here, an analog signal, and then we assign this value to either one, this level or the other level, depends which one is closer. And then we really modify the information from here to here in the quantizer. And that's the error that we introduce, and people call this quantization noise. And in every single sample, we introduce a small error because we are quantizing the information. Obviously, this information this error is very systematic, especially if you have a sinusoidal signal. The errors are always the same, and they are repeating every number of clock periods. However, in general, this information is or this error is more like thermal information or thermal noise, because the input signal in the practical applications is kind of random. It's quasi-random. And then the quantization errors are going to be quasi-random, and the energy of those quantization errors is spread more or less evenly in the entire frequency of operation. Then this is considered kind of a thermal noise, thermal error, but this looks more like a regular thermal noise that we have in our devices. Okay, the Nyquist ADC, or the line ADC in particular, is so-called a feed-forward amplifier. There is not global feedback from the input to the output, or vice versa from output to input. It's straightforward. We put here the quantizer, and then when we quantize the signal over here, and then we are adding this quantization noise over here, and then we are going to make two representations of the output. We're going to represent this one as an ideal output, which is similar to this input over here, and the quantization error is represented right here because this is generated in this quantizer. Then quantization error is represented in this way. Quantization error for a real signal is going to be kind of a random, and we have the power of the input signal here. If we put a tone here, we have the power of the signal, and we need to always compare the power of the signal versus the power of the quantization noise we are generating from this. This analysis is done in many different books. You can easily check that the signal to quantization noise ratio depends very much on the number of bits you use in this quantizer, where the number of levels is 2 power n or 2 power n minus 1, depends how you quantize this information. But the number of bits times 6 plus 1.76, that's the expression for the SQNR in dBs. Of course, if you want to improve the signal power versus quantization noise power, you need to increase the number of levels that you have in your circuit. And this is one of the reasons for increasing more the number of levels you have over here to improve the SQNR. Of course, SQNR is not the only noise that we have to consider. SQNR is just the noise introduced by the fact that we are quantizing the information. But we have also thermal noise in the devices we have over here. We have also the clock is not perfect. We have a jitter. Jitter also introduce some noise, etc. We have a different kind of noise component. An example of an ADC. I'm not going to discuss the details of this ADC. That's not the point here. The only reason for putting this slide over here is because this is usually the pipeline is composed by several stages in Cascade. In many cases, they are identical except the last one. The last one is more relaxed than others, and every single stage has two components. Okay, this one is fundamentally the part that is going to resolve. For instance, talking about this guy is going to resolve the first 0.5 bits or 3 bits or whatever number of bits we have here, and we have a sub ADC that is very relaxed. It's only 2.5 bits or 3 bits. It's not very difficult to do this. And from this one, we're going to process right here is this information that is quantized over here, and then we convert this one back into analog with a DAC. The nice thing about the DAC is that the DAC do not introduce quantization noise because this information is quantized and the output of the DAC is quantized, and then this DAC is this guy is our friend, and then this is a very good replica of the information we have here in the sub ADC. We resolve the first bits, and then we reconvert this information right here. Now, what we are going to process is fundamentally the difference between the signal and the signal reconstructed by this one over here, and this is kind of a differential device. And the signal power over here is much smaller because we take the difference of this one and the first approximation in digital that with discrete levels of that signal over here, and this is the so-called residue signal here. It's much smaller. We could process this information here, but if you want to make your signal stronger, to be more immune to the noise of the following stages, we usually amplify the signal by a certain factor over here, such that we relax the specs for this because the signal was amplified by this. You see, effectively for the signal itself, the signal is amplified here by a certain factor, and here it's much stronger, and then can tolerate more noise from the following stages. Of course, the signal is not saturated here because we are subtracting this part. Just for a very simple example, we can use just 1.5 bits per stages. This means those two capacitors are connected to the input and pre-charging the input, and later on, one of those guys is connected to the output, and this guy is connected to a certain voltage right here as a reference to do the to generate the residue signal over here. Fundamentally, this circuit, what this circuit does is we have an amplifier here. In theory, C1 and C2, they are identical, and there is an amplification by 2. And we are subtracting here the voltage that we have over here that result from the previous bits that are resolved by those sub-ADCs. The output of those decided which level is going to be added here to generate the residue. And then the operation is very simple. We just need to have an amplification by 2, and over here we just amplify by 1, whatever voltage we select here from the bit that we resolve in this ADC. Then I don't know why we are spending too much time on this thing here. Maybe this slide can help us to understand this. The issue is that we have a lot of errors, practical errors in this operation. We have the fact that the capacitors are not identical. There is a small mismatch between those capacitors. We have parasitic capacitors right here. Our operational amplifier is not ideal. The gain of this operational amplifier and the velocity of this one is not infinity. And then we have some errors introduced by this guy. We have offset in this amplifier. We have a mismatch in the transistors, internal transistors, and we have problems with the switches. The switches have some resistance, etc. We have a large number of limitations right here. If you spend a little bit more time, like 1 week, and you analyze this particular circuit, so simple, including the loading or so, you'll see that the resulting equation is much more complex than this equation. You see that the operational amplifier do not have infinite slew rate, cannot respond immediately. They don't have an infinite bandwidth. This is something that is mentioned right here. We have also the transistor, we have something that is so-called slew rate right here, that will affect this exponential function here. And this exponential function is nonlinear. And if this exponential function plays an important role in the definition of your results, now we're in bad shape because this is nonlinear. And we have also some other effects, like the gain of this amplifier is not infinity, mismatch in the capacitors, offset in the amplifier, etc. And in reality, is much more complex. In theory, what we are doing, sorry for not having time to elaborate more on this, but what we are doing with this system is we are segmenting our signal. Our input signal is this axis over here. Now, the sub-ADC that we have, the very first one, let me go back to this. This one over here, if you want to how strong is your signal is above BR/4 or below negative BR/4 or is in between. We have two levels right here that will give us the information where the signal is, in which segment is this. And then we take here BR/4, and then the sub-ADC is going to tell us if my signal is in this range, or is here in between, or is right here after this. And then the ADC will do 3 different operations depending very much on the information we get from the first sub-ADC. We are here in the middle. That means the information is, the input signal is relatively small. And the only thing we are going to do is we are going to amplify the signal by 2, since we are not going to hit the full range. And then we just amplify this 1 by 2. But if we are here, my signal was in this range over here. Now we need to have a good interpretation of the output. What we are going to do is the original information over here is going to be shifted. That's what the DAC does. And then we amplify this 1 by 2. If we are here, now we are going to shift the information into this range over here and then amplify this by 2. However, if we have multiple parameters, each one of those is going to affect this curve in different ways. Capacity mismatch will change the slope of the different segments. We have a finite gain in our amplifier. This will have more effects on large signal over here. We'll also have some effects over here. Not too much effects in this region over here. We have more effects into this region over here. Remember, the product is non-linear effect. Will affect fundamentally large signals and high bandwidth, fast frequencies. That's where the signal is going to be affected. High frequency will be more affected by this. Offset, not really a major problem. You are just shifting this this curve. It is not modifying the shape of the curve of the residue curve, and you can correct for this. But the other thing is amplifier. The amplifier is not really linear. It's going to produce some non-linearities in this part and in this part, especially for large signals. And based on this, we need to really identify what are the most critical parameters. One of them is the slew rate. Slew rate, you can see this is signal dependent, depends on the output voltage and depends on the ability of your amplifier to move from one value to another value, the output. This depends on the amount of power that we can deliver, and depends also on the loading. This is one of the main enemies. And the other one, of course, is gain. Identify if we are going to design circuits. Always, my recommendation for all of you is to start with the very, very basic cell. Okay? Like this very simple amplifier. First, use a single stage, use one differential pair that is doing fundamentally all the operations. And we need the bias current over here, and we need to terminate this differential pair with 2 bias currents right here, with a current that is 50% of the current we have over here. Now, if you plot the voltage you put at the input versus current, of course, this device is linear, but only in this small region over here. A good reference for those guys is the overdrive voltage, the VDSAT. Up to VDSAT over 2, you can consider your amplifier is kind of quasi-linear. But at VDSAT, you start having seen here some saturation. You decrease more the differential signal, or you increase more the differential signal. This is not longer a differential pair. One of the transistors will be off, and all the current will flow across the other one. And then what you have over here, the current over here will be 0, for instance, and then what you're delivering is just IB. And in this case, this is completely on. This current will flow across this device. Now you have here 2 times IB. You have IB here, and then the current you may extract from this part over here is only IB. Those guys are not really doing anything. This is constant, but are needed just to terminate this differential pair and to absorb the bias current that we have in the circuit. Okay, bottom line, we have 2 regions over here, depending very much on the overdrive voltage. If we are in this region over here, we can assume the circuit is in the slew mode, where the current is no longer controlled by the input voltage, but is fundamentally controlled by the amount of current that you put over here and in the terminations. Only when the voltage is small is when you consider this guy is in a linear regime. Now, in ADC specialty pipeline, everything is done with capacitors. We have a capacitive amplifier here, very, very conventional. Since you don't have resistor right here at the output, there is no need for a buffer at the output. You can have a so-called transconductance amplifier with no low output impedance. Then you can represent your operational amplifier as a voltage control current source. And over here, you want to reconnect this terminal after you pre-charge the capacitors. You reconnect this terminal to VDAC or whatever. And fundamentally, you are applying a pulse at the input. You apply a pulse at the input. And let's assume that the capacitors were discharged, just to understand this operation. Apply a step here. Now this voltage moves up. The operational amplifier do not react immediately. And then this voltage will follow very much the variation you have over here. And this voltage will also move right here. The operational amplifier starts just generating the current right here. If this was positive, now this will generate current in this direction. And the current will flow across those two capacitors. And we start discharging this capacitor here. If you look in this node over here, this voltage will have a spike over here. And the current over here will start discharging this. The discharge is fundamentally given by this current and the value of this capacitor, since this is fixed. And then you start discharging this. Then how fast you are discharging this node to move the operational amplifier into linear regime depends very much on the bias current and the value of the capacitor. If you want to make this faster, there are only two parameters that you need to optimize. You may say, okay, why not to reduce the capacitor and then that will make this one much faster. This, as I mentioned before, this is just part of the problem. Because the other problem is thermal noise due to the switches. Thermal noise due to the switches is KT over C. And then C must be set based on the thermal noise limitations. Then C is fundamentally something that we cannot set for a slew rate. This is set fundamentally for thermal noise. And then the only parameter that you have is IB. Then the only thing you need to do is, you want to increase this, you need to increase the power consumption. And then your design probably will be power hungry. We need to find some ways to improve this thing over here. The bad news is that the previous slide is just an indication of what may happen in the system. In reality, the problem is much more complex because we have a capacitor here, we have a capacitor here, and we also have initial conditions in all those capacitors. Well, the bad news is that when you apply a step here at the input, the voltages in different nodes are affected by the initial conditions, and you have a much more complex operation. The other bad news is this capacitor plays a very, very important role here, because you may imagine that the amplifier will move to a steady state condition only when this voltage approaches zero. And then we have this current here, and this current is going to be split. Part of the current is taken by this guy, and the other part will move into this thing here. As a result, for a slew rate, from here to linear regime, which is the overdrive voltage, the amount of current that you are changing, you are using for discharging this, is not IB. It's IB, but you have also this part over here that is affected fundamentally by CL and the parasitic capacitor you have over here. It's much less current that you have over here. And then the time for a slew is increased by this part over here. Again, you need even more current if you want to make this one much faster. The other issue is linear settling. I'm not going to elaborate too much on this slide, but you have operational amplifier here with one parasitic pole, and you have another pole here at the output. You have two poles in the system, and this is in a feedback with the capacitors over here. Now, the settling error you can find in many different books. The settling error is fundamentally given by the GM divided by the total capacitance here at the output, which includes this and the capacitance you have in this node over here. You need to account for this, and also you need to multiply this one by the feedback factor, and then times T. You have only one clock phase to do this, to reduce this error as much as you can, and fundamentally the error after the one clock period is given by this equation over here, which depends very much on the gain boundary product of your circuit, depends on the feedback factor, and depends on the clock period you have over here. And this error, of course, must be smaller than the resolution that you expect to have in the following stage. And this is one of the big issues when you are resolving different large number of bits at the output. Bottom line, if you put this one as a function, this equation as a function of the requirement for GM in this guy over here, GM have to be larger than this equation over here, which depends on the number of bits, depends on the capacitor, inversely proportional to the feedback factor, etc., and directly proportional to the clock frequency. More clock frequency means you have to use more GM in your system. Really, really an issue. Effect of the initial conditions you can see here. You don't have, if you pre-charge the capacitors to different values over here, in the very worst case, if the capacitor is pre-charged to the opposite value that need to settle, you have a lot of time for just for slew, and then only this part here for linear settling. You need to optimize for slew, you need to optimize for settling, and the two optimizations are different. There are many circuits that companies are using. This is probably one of the favorite structures for analog devices. I saw several products and several papers from this group that is that use this topology, this so-called telescopic. Telescopic is a very old circuit, and this is very, very effective if you don't use the auxiliary amplifier right here. You have only this transistor and this transistor. Now the signal goes directly from the input to the output. The current here flows only across this Cascade transistor and reach the output. Fundamentally, in this circuit, you have the GM of the differential pair. You have one parasitic pole in this node, and you have the dominant pole here at the output. Very effective. GM is just given by this guy over here, and then this has a relatively good output resistance, in this direction because the Cascade transistors. And definitely this topology give you good performance. If you want to have more DC gain, you can use this boosting gain over here, putting a very simple amplifier from this node to this node. Instead of having the variation right here, you transfer the variation into this gate, and that results in more gain in your circuit or higher output impedance in your circuit. But this is not going to give you more current capability. It's affecting fundamentally the output resistance of your circuit. You increase the DC gain of your circuit, but not necessarily the velocity. The other thing that we need to be aware of this is that you are adding parasitics right here. The frequency of this pole will move down a little bit, and also you have a pole right here. You have a loop right here. You need to be careful with the stability of this loop over here, and that usually introduces a pole zero pair that probably somehow your specifications at very high frequencies. This circuit has limited signal swing over here because you need to accommodate signal swing for this. You need to accommodate headroom for this. You have 5 transistors in this on top of each other, and then you have a relatively modest headroom for signal swing over here. It is a good option, but there are some limitations. And people use also the folded Cascade. Folded Cascade was invented by Harvard Semiconductor back in the 66, 67, using bipolar devices. Still is very good. Fundamentally, this circuit is similar to the telescopic, but they decouple the differential pair from the output, injecting the signal, the current here into this Cascade node, and this signal here into this Cascade node, generated by this differential pair over here, will make the current to circulate across this here, and then the output is not directly correlated with this part over here. It is more isolated, and then the operating point over here and the signal swing over here is not limited by your differential pair. But this circuit is more power hungry than the previous one, because now you need current for this arm and current for this arm, and then it's not necessarily very, very efficient. It can be shown that in this paper, it's a study of different architectures. The slew-rate, only 50% of the current is used, mainly because this is only pure DC, used to terminate this part over here. It's a good option. Another one is using here a current mirroring your AC signal into this arm over here, Cascade transistor here. Power consumption is kind of similar to the previous case, but you can add here an amplifier that can give you a little bit advantages. The circuit has a little bit more power efficiency, because if you put here an amplifier, you can reduce a little bit more the power right here. at the expenses of increasing a little bit more the noise of this guy, and then can give you probably a little bit better slew performance. This is a very nice addition using a dual differential pair, this one and this one over here, and then the input over here. Now this guy over here connect the signal right here into those cascade nodes, and then you ask this guy also to control AC current, not only DC. And the PMOS transistor inject differential pair, inject current right here, and then it's collected right here. Now your transconductance increase because you have the contribution of the two. And now this arm is handling AC signal, and this arm is also handling AC signal. Your slew rate increase is better than the other two cases, and you have like a two transconductances working in series. One is converting the current over here, and then you have one OTA here, and then this one over here, and through this one over here, and the current is combined right here. In fact, the GM is adding, you have an addition of this. If you work with this one properly, and you try to equalize this part with this part, fundamentally, you're going to double the GM of your circuit. And in general, the use of the power consumption is better than the other cases. Nothing is free here. Okay, you may notice that the input capacitance over here now is increased. That's the trade-off. You need to evaluate this because now you have input capacitance from this guy, you have input capacitance from this guy. There's no doubt that the input capacitance over here is going to increase. You can tolerate this, that's fine. Something that crazy people do is they split this one in multiple pieces, and they take current over here. This is kind of a folded cascade. This part of the current over here. Part of this current over here, for instance, this current gets mirrored here and gets mirrored right here. This guy, together with this one and this one, is the circuit with current mirror. And even more, you can use this current over here. You can put another transistor, and then you can ask these guys also to process information. This is like a class A circuit. This is equivalent to have 3 operational amplifiers working in working together. You have some poles, and then you combine this equation and you put as a pole zero in the format of pole zero pairs. You will see that you have fundamentally 3 poles, and you have 2 zeros, 2 compensation zeros in this architecture. You compare all of them, you will have some surprises because the circuit with the so-called 3 paths will have a much more gain than the others, and then the static. This is a step response for an operational amplifier using all technologies. The 3 path is a little bit faster. The 1% settling time is somewhere here. The folded cascade is a little bit slower and with less gain. The complementary is a little bit better. The current mirror is a little bit better, and the 3 path is a little bit better. Okay? And there are different options, and definitely you need to evaluate those options. Something that has been well accepted in current technology, so-called recycling folded cascade, which is a special case of the, as I mentioned before, those guys are not really helping with the AC signal. See, the AC signal flows only into these trajectories. It will be nice if you can, if we can ask those guys also to manage the signal over here, and then splitting this in 4 pieces and mirroring this signal right here, and having here using this one as a kind of a current mirror. You mirror this one, which is out of phase with respect to this one over here, but over here you recover 180 degrees. You have an inversion here, and adding the 2 components right here will increase the GM of your circuit. You put here certain gain. Now the transconductance is whatever transconductance over here multiplied by 1 plus K. That's a very effective way of increasing the transconductance of your circuit and also the slew rate of your circuit. Okay? You're fundamentally combining the 2 currents, and that will increase the current in this case. If you compare the regular folded cascade topology with this one over here, you can see that the regulated can provide much more current. That means you are going to charge much faster the transistors, and the current use reaches 0 much faster than the other one. That means you recharge the capacitors very quickly, and then your settling time is much faster. That's what happened over here. Of course, because you have another trajectory, you're sacrificing a little bit the phase margin. That's something that you need to consider here. You need to have always a phase margin better than 45 degrees to avoid ringing in the step response. And this is a comparison of how fast could be the regulated cascade. This is for the same power consumption versus the folded cascade over here. Settling time is faster, and slew rate is much faster. You can notice in this comparison over here. How you combine signals, all this is going to be reflected in the performance of your system. Well, for the same power, you built a system, an ADC, with the folded cascade. Now you get a certain linearity. In this particular case, something like a 60 dB of linearity. But if you have a faster response for the same clock frequency, now the distortion is much smaller because the circuit can reach steady state much faster. This is more than, you compare this one with this one, it's more than 5 dBs. The distortion, and this is almost 1 additional bit in your ADC. You really want to move forward, something that you have to do is to help your operational amplifier, maybe 2 stages. Okay, it's a good idea to have a class AV. Class AV has a nice property. The current that you have in the ADC increases, is not limited by the bias current, increases when you apply large signals, and then you have more current to charge faster this capacitor and the other capacitors. But on top of that, if you want to really improve this, something that you can do is you can add another part over here with a circuit that could be class B or could be class C. That means if the signal is small over here, you don't have any current. If the signal is large, you provide much more current in your circuit. Then the biasing of this amplifier must be such that the current, when the signal is small, is almost 0, but when the signal is large, that's when you need it. To help your circuit with the slew rate, the current over here could be even much larger than the current of your regular amplifier. If you want to see the details, you can check this paper over here. Amplifier could be used as a regular amplifier, cascade topology at the input to have a large gain over here, and second stage is a class AV. Signal is injected here, and through this capacitor is also injected into this class AV. Large swing, because you have only the VDSAT of this one and the VDSAT of this one, limiting your signal swing. If this is a second stage, probably you need a kind of a Miller compensation here. And this one is just enables the information, transferring this information from this node to this node without compromising the operating point. This voltage over here sets the operating point of this transistor. This voltage must be lesser than the threshold voltage. I'm sorry, this operates in linear regime. This is not the circuit, that is the auxiliary circuit. For the auxiliary circuit, you need a very simple amplifier, must be very fast. For that reason, we use resistor here that minimize the parasitic capacitor right here. And then this goes into another class AV amplifier, and this voltage bias this transistor and this transistor enough region. The operating point for this one is set such that the bias current in those guys is very, very small. It's fundamentally class C or class B. And only when you have a large spikes here at the input, you have the synonymous of large signal at the input, now generate large signal right here, and then those guys must have a very decent dimensions to generate large signal only during those spikes. The circuit start, the input of the op-amp start reaching a steady state. Those guys are fundamentally off. Only we want to use only this spike. Obviously, AC response for the circuit with or without this additional circuit are very much the same because that circuit is not adding too much. And those are cadence simulations. This is the current generated from the auxiliary circuit. And this is the current generated from your core ADC. Now, why this is important? Because this guy is going to provide a lot of current, but fundamentally is not adding a static current. The static current is almost 0. It's only dynamic current. And then the increment in power consumption is minimum. That's the benefit of class B, class AB, class B, or class C amplifiers. This is my favorite plot over here. That circuit is very fast, reacts very quickly when you apply a step at the input. The signal is very large, but when the circuit starts just moving down, try to reach a steady state. Now this path is much faster. It's not precise, but it demands a lot of current over here, but decrease very quickly, much quicker than the regular speed of the operational amplifier. Those are experimental results. I'm not going to discuss those things here. I prefer to discuss this. Those are experimental results, measurement results for an ADC. The student was able to turn on and turn off the auxiliary circuit. Those are the results without the additional circuit, just the standalone amplifier. The harmonic distortion is -53. The third harmonic distortion, -53 dBs. But when this additional circuit is activated, now this is -64. You see the difference between this guy and this guy is more than 10 dBs difference in linearity. That's more than 1.5 bits. And this is the plot in frequency versus harmonic distortion. This is the slew boosting, and this is the normal one. Of course, if the signal is at low frequencies, you don't have a lot of demand from slew rate because your signal is slow. When you start increasing the frequency, now you demand more slew rate. And this guy is just the amplifier itself, and this guy is helping this with the distortion in very demanding specifications. That's what we wanted. Okay, that's just more results from the actual amplifier. And this is the result when you implement the ADC. You see, for instance, here the amplifier, the power consumption for the system is you can optimize. This is less than it's 18, a little bit more than 18 milliwatts. But this is achieving 64 dBs of SNDR measured at high frequencies, because that is close to the Nyquist frequency. That's what you need to improve the performance. Now, if you see, for instance, this work over here, it's just a little bit less power, but the linearity of the performance is 56. You see, for instance, this one over here is more or less the same thing. This is even just SAR ADCs, but the performance is much limited than this, and so forth. Same thing. This is a little bit better, but this includes calibration. This does not include calibration. Okay. Well, bottom line, you need to improve your performance for settling time and for slew rate. If you're going to design Sigmadelta modulators, the history is different. Because in the Sigmadelta modulator, you have a continuous time filter here embedded in a closed loop. This belongs to the category of closed loop. And what you have in the feedback are fundamentally DACs here, the output signal over here, and you are feeding back information here to the input. Now, what is important in the Sigmadelta modulator is to have a large loop gain in the boundary of interest, the gain of all this thing over here. If you have a large loop gain, the performance from input to output depends fundamentally on the linearity of this building block over here, the feedback element. It's basic feedback theory, basic control theory, and can tell you that this is true. Okay? Everything depends on the feedback. But the issue is that you need to have a large loop gain, and the loop gain cannot be provided by the DAC. Can be provided only by the filter. Then you need a filter with a large gain, low pass filter or band pass filter. Depends on what kind of ADC you are going to design. This is not going to provide gain, because this is just changing the format of this information into digital format, and this is returning back from digital to analog. Okay? Then the design of the filter. Now, because this is continuous time, this is an active RC. And this is fundamentally dictated, the performance is dictated by the performance of the ADC. Now, the issue here is that if you notice here, most of the power consumption is coming from the filter. You want to have something interesting and save power. That's the element that you need to save. For instance, one example is a quadratic filter, where the DC gain of this filter is something like a 50 dBs or so. Then you need to have a large gain in the band of interest for the circuit to be practical. Okay, the Miller amplifier is one of them. Is one option. Transistors, you really want to reduce flicker noise. That's a good idea. And having this Cascade transistor here with resistor is also a good idea, because you increase more the gain of the circuit in this node. You have a more gain from here to here, and that increases your circuit. And this also eliminates or minimizes the flicker noise of M3 and M4. It's a good idea. The only thing is your dominant pole is dictated in this node over here. It may not be a very fast solution, but almost everybody is using right now is the so-called feed-forward compensation. Feed-forward compensation implements so-called phantom zeros, because apparently there is no zero here. We have one amplifier with two stages, and we have over here in parallel we have this amplifier with a single stage. If you work with the math of the two topology, you will see that this overall performance has two poles, this one, and one zero that is generated from this guy over here. Then this do not require Miller, do not sacrifice the bandwidth. The only thing is the phantom zero must be placed at relatively high frequencies and at strategic location. Just one example. This paper in 2010 is just one example that people are implementing this in this. The reuse, this is the first stage. This comes into this transistor, and also the other output comes into this transistor. This one and this one are the second stage. And to reuse the current, there is another amplification here. This one and this one, biased by this one over here. Fundamentally, this guy has two paths, one P and one N, to increase more the transconductance of this guy. And the feed forward is implemented with this guy over here. Those are the inputs, and this guy over here inject the signal right here. The rest of the transistors are for common feedback. This is just another example. This paper is quite important in this area. Actually, this company, when they presented this paper in ISSCC, this was an startup company, and that was acquired just after this, after ISSCC. The amplifier they were using is a 4-stage amplifier right here. This is the main amplifier. And this part over here, together with this part over here, and reusing this one to convert this one to class AB, is fundamentally feed-forward compensation. In order to have a better control on this node, which is the one they want to have as a dominant pole, they use here some kind of a Miller compensation here. But most of the compensation is done fundamentally to the feed-forward compensation. And they achieve a very good performance. The dynamic range of this device is 80 dB, which is outstanding. You see another example, already 2017 in Journal Solid State. You can find this MASH Sigmadelta modulator. It's a two loops ADC. Also, the amplifier has 4 stages. In this one, you don't have Miller, one feed forward, and this part over here is also class AB. Another feed forward is fundamentally feed forward compensation. You have your main path, and you stabilize this one through different feed forward stages. And of course, you need to be sure that the unity gain frequency, your phase, is good enough. This is just the performance. Incredible, because with this very large gain and wide bandwidth, the distortion is well below 80 dBs in a wide bandwidth up to 50 megahertz, and the performance, the signal to noise plus distortion ratio, is almost 75 dBs, which is more than 11 bits, and the power consumption is relatively modest. For that reason, I added just a couple of slides for a class AB. Okay. This paper is a very old paper. I think it was published back in '86. But I consider this one of the smartest papers. Unfortunately, it's not easy to read this paper. And for that reason, this paper or this technique was not very popular till the 80s. One Gray and Mayer used a simplified technique and then put this one in their book on IC design. And they highlight what are the main properties. But I call this circuit, when I'm teaching this in TXNM, as a magic circuit. Magic circuit because this has several properties that is very, very difficult to believe. And this signal over here is directly connected to this. But the problem is how to bias this properly, and on top of that, how to transfer this information from here to here. And this is the circuit that is doing this. My first reaction when I saw this one say, oh, this is just a common gate. Okay. And then the impedance over here is 1/GM of this transistor. That's low impedance. I'm killing the gain in this. But no, in fact, it's not. It is true that this is just 1/GM EG series, but this circuit is feeding back the current across this one over here, and then return back the current right here. As a result, the current you are taking from this one is minimal. It's just the current that is leaking right here in the bottom. As a result, the impedance over here, CV, is large. As long as the impedance seen in this direction is also large, and then all the current recirculate here, and you're not taking current from this guy over here. And then on top of that, this voltage over here, set the voltage over here, if you select this properly, this voltage over here is just VGS above this level. That's the level that you will put over here. The biasing of the transistor is controlled by this guy over here. The biasing of this one is controlled by this. You need to generate the proper voltage here and the proper voltage here, and that's it. That's what I mean. The circuit is really, really magic because it's a kind of a short circuit for AC signal. And with this voltage and this voltage, you can set point of this one and this one. The only limitation is, of course, the impedance. If you are using here Miller, now, unfortunately, this impedance is not. It's not very, very large. The impedance seen in this direction is large. But if you have here a capacitor or something like this, now the impedance is going to reduce. It's not just 1/GC, but it becomes 1/GM. That is much smaller, and then the gain of your transistor right here, your amplifier here, reduces and reduces here too. Then the response of the circuit for a very high frequency application may not be what you expect. But you can do something here. I mean, you can use a feedback. Here, a kind of a small resistor and capacitor in parallel, relatively large resistor. The capacitor is going to pass all the AC signal over here, and the resistor is just in order to generate the bias voltage across this. You take here the average. It's a kind of a common mode feedback. You put a large resistor right here. You take here the voltage that you want to have in this transistor over here, and then you compare this one with the reference, and comparing this one, those two guys with the reference, now you set the voltage drop across this. That's another way of implementing the Monticello circuit, and then this guy do not suffer from that because at high frequency the capacitor is going to help you. Okay, you can do simulations for multiple tones, in band, out of band, and you can see that circuit can give you 5-6 dB better for in band information. For out of band information, is even better. Okay, since time is money, I don't have I didn't want to include more details right here, but fundamentally, if you want to implement amplifier for pipeline ADCs, what you need to optimize is the pulse response of your circuit. And then the pulse response is fundamentally a matter of slew rate and linear settling, GM, phase margin, and in this case, it's a matter of optimizing IOVC. Yeah. Even if you don't have very large gain, it's fine, because if the errors are systematic, are not signal dependent, those can always be calibrated. You don't need to achieve a very large gain. As long as the gain of your op-amp is kind of a linear, that's fine. You can calibrate for those errors. And a Cascade amplifier is something that give you this. However, for Sigmadelta modulators, the history is a little bit different, because what you need to optimize is an amplifier that is resistive terminated. That's a little bit more difficult. And of course, if you want to optimize for power consumption, Class AB amplifier is always the way to go. Okay. Of course, you also, because this is a closed system, you really need to have a very linear DAC, since most of the properties of the Sigmadelta modulator depends on DAC linearity. Some people use even here certain kind of randomization. They linearize this at the expenses of adding more noise due to randomization processes that you may have over here. Of course, loop stability. This is not stability of your op-amp. This is entire loop stability. It's another big issue, and for that we use a fast path that has to be properly set to guarantee the system stability. Okay, I think that's all what I want to say in this seminar. Of course, feel free to send me emails if you want me to elaborate or provide a little bit more information on any of those topics.
Okay, thank you. Thank you, Professor Silva Martinez, for excellent talk and presentation. High performance and the issues on the op-amps and their optimization. It's quite a very nice material that you covered, and we have a few questions from the audience here. The first one has to do with calibration. Jeff Shee asks about digital calibration. So what is the widely used digital calibration algorithms? What are the algorithms that can be used in industry for pipeline ADC, especially for non-linearity calibration? So it has to do with the pipeline with ADC.
Yeah, one of the issues is we need to differentiate between signal-dependent errors and signal-independent errors. We are talking about calibration of, for instance, capacity mismatch, or we are talking about offsetting the operational amplifiers. I mean, those are not very, very difficult to calibrate. If you want to do this online, there are excellent papers that cover this. In most of the cases, in general, in this kind of systems, the only problem is how to measure the error. We need to have an indication of the error. And with that error, we can put this one in a kind of LMS algorithm or something like that, just to minimize that error. There is an excellent paper, excellent presented by the magazine of Jonas Solid ago. What's the name of the professor from Davis, University of Davis in California? Oh my goodness, my memory. Okay, but you just search for in the magazine of Jonas Solid State, where there are only tutorials. You can find the discussion of the most interesting calibration algorithms in pipeline ADCs. It fundamentally is just a matter of measuring, identifying the errors and trying to for those errors using LMS algorithms. Right now, many companies do not like to do that, because if you have a broadband application, the bits are becoming very fast, and even a single multiplication very expensive, especially if you have a high resolution. So the price that for very high applications, very simple algorithms are used, although those may not be very precise. We talk about calibration of linear or signal-dependent errors. That's even more, because you need to implement a kind of recursive polynomial, where the polynomial is function of the signal, the square of the signal, cubic of the signal, and so forth. And then implementing this is almost impossible for fast applications. For relatively low speed applications, you can still do that, but not for very high frequency applications. Now, in my group, what we are doing is trying to measure the error using a blind algorithm, calibration algorithm, where what we do is fundamentally we don't measure directly the error, we measure the error. For instance, in a practical application, your signal is not covering the entire bandwidth, it covers only fs/4 or so. Now, the leakage of information that you have between fs/4 and fs/2 are the effects of the nonlinearity that fall in that band. and then measuring the power of this thing and using this one in the calibration algorithm, and then using a blind algorithm, multidimensional, you adjust parameters in digital to try to calibrate for that error. And the aim is just to minimize the power that is in the stop band of your ADC. That's the way we address the problem.
Okay, yeah, it's a whole Pandora box on calibration. Thanks. Now, another question from Marcelo Dalalba. His question is regarding the multipath differential amplifiers. He says that multipath differential amplifiers to reduce distortion by increasing slew rate might result in higher noise factor and then higher noise reference to the input. So the question is, doesn't it require higher input capacitance, pushing the slew rate down as a result?
Okay, let me comment on the operational amplifier with multipath. It is true that you are adding more transistors and you're adding more paths, and your overall noise, input referred noise of the circuit could be a little bit higher than the other one. However, when you are designing a real ADC, usually the most demanding specifications are from linearity. That's the main limitation. I'm talking about high frequency applications, more than 100 megahertz, where the timing for settling is in the range of nanoseconds, maybe tens of nanoseconds. If we are targeting 1 gigasample per second, now the time for every single clock that we have for linear settling is 0.5 nanoseconds. And then the main errors are coming from linearity, and that's problem number one. Problem number two is, of course, quantization noise. Quantization noise because you have to increase the number of bits. Usually, we sacrifice a little bit of power consumption in order to reduce the thermal noise. The thermal noise, in my experience, is not so difficult to put something like a 6 dB below the quantization noise, your target specification. In that way, even if you sacrifice a little bit of more noise at the input, then you have a certain buffer. My experience is that the most problem number one is linearity for broadband applications.
Okay, thanks, Marcelo, for your question, and thanks, Professor.
Yeah, thanks, Marcelo,
for your question. There is another question from Kamlesh Singh out from the internet. Question is, what should be stability requirement of the OTA in the continuous time Sigmadelta? Should it be stable in unity feedback?
Well, usually not necessarily, because the unity feedback is not necessarily the best, in my opinion, the best way to measure the stability of the amplifier, because this is operating in a very different feedback factor. In the operational amplifier, I guess the unity gain frequency of the circuit usually is even with a feedback is even beyond the unity, the clock frequency, or relatively close to the clock frequency, and because this is oversampling ratio, this is well beyond the unity gain frequency of your loop. In general, you have to prove stability with the feedback that you wanted at high frequency. Then you have a resistor on the output, have a capacitor in feedback, but the capacitor, of course, at such high frequency has a certain impedance together with the input impedance that you have at the circuit. Is loop gain what you need to guarantee with the proper feedback.
Okay.
You have a relatively large feedback. Usually, the stability is much more demanding what we believe.
Okay. I think the last question for today's seminar comes from Zhu Yang. he and other viewers here, thank you very much, Professor Silva Martinez, for your nice presentation. And he has a question to address you. How do you compare these amplifiers you presented to the simple inverter-based amplifiers? In your view, what is the future direction of amplifier design for ADC designs? It's a very broad question, but it has to do with what is your view of the future directions of amplifier design for ADC, and also how do you compare this with simple inverter-based amplifiers?
Yeah, I'm going to start answering this question, but I will really love if you can specify a little bit more about the amplifier using inverters, and you mean use inverting type with the P transistor the source of the P transistor connected directly to VDD, and the source of the N transistor connected directly to VSS, or you are talking about use a differential pair with current sources upstairs and downstairs, like the one that I presented here. But anyway, I'm going to start assuming that the question is related to the inverting amplifiers. Let me. I was just trying to find one slide.
Okay, you have many topologies.
Okay. Right here. Okay, I'm not talking about this because this is single stage amplifier. I'm talking about the case in which you have an inverter like a digital inverter with a transistor, P transistor upstairs and an N transistor downstairs. That is a work done by Bram Nauda. His PhD thesis was on inverting type of amplifiers, and he demonstrated that you can build very, very power efficient systems. On top of this, the GM of those devices has the combination of the contribution of GMN and GMP, which is very good for from that point of view. The gain is not very, very large, but you can accommodate this with some other amplifiers in Cascade. However, my main concern in this kind of applications is, especially I'm talking about high resolution ADCs, more than 10 bits, is the poor power supply rejection ratio. You may argue that we have two transistors connected, for instance, to VDD, and if the VDD is noisy, now you have a lot of noise going into your amplifier through this device or this device here. But in that particular case, it's class AV, and then the transistors you have over here are also very sensitive to VDD noise. Only the mismatch of those guys could be easily produce a signal feed through that is larger than the resolution you're looking for. Same thing with the current that you have, or the noise that you have in your ground. This will also be fed directly into your circuits. PSRR of those circuits is not as good, and I don't think that you can achieve high resolution. I guess those solutions using single amplifiers, it have to be tested with noisy power supplies in a real system where you have your system being surrounded by a lot of circuits, and the supplies may not be very, very clean, and also the ground, global ground, is not going to be very clean. And then my guess is that those circuits will be limited by that.
Okay. Well, I think we had plenty of information on this talk today. I would like, again, on behalf of the IEEE South Brazil, chapter here, to thanks Professor Silva Martinez a lot. Indeed, it's been a quite long time. We have been asking his presence here to deliver this very, very nice, talk on all the complex topology that he review today for you. So thank you very much, Professor Silva Martinez. Just to let you know, IEEE friends, that in the subject of continuous time pipeline ADC, which is part of the first part of this Professor Martinez talk, will be also addressed in the solid state circuits webinar, which will be held on November 20. That's going to be delivered by Hajime Shimata from Analog Devices on continuous time pipeline ADC for wide bandwidth wireless circuits. So with no further ado, I give the floor to you, Professor Silva Martinez, to say the last words to the audience here. And on behalf of my colleagues in the board of the chapter here, myself, Professor Sandro, Professor Felipe, Professor Paulo Aguirre, Professor Vinicius Camargo, all here from South Brazil, we will be having our seminars of distinguished talks held in this channel. I turn the floor to you to say, let's say, some messages for the audience that joined you today, and be able to see you in this channel later on. So thanks.
Okay. Well, thank you very much first to the organizers. Sergio, thank you very much for the invitation. Well, I don't want to say names, but thank you to everybody, and thank you to the audience for following this presentation. And feel free to send me emails if you have any question, or you want me to elaborate a little bit more on any of those topics. And it was a real pleasure to be in contact with all of you. I was very happy today.
It was all pleasure, and certainly to the light of all the people working in this field of ADCs and the complexities of the old friend amplifier. So thanks very much again to all of you in Cyberland, and especially to our distinguished speaker of today, Professor Jose Silva Martinez from Texas A&M. So keep subscribe to the channel for the upcoming webinars, and also in the Solid State Circuit Society and EDS webinars are being mailed directly to you by the society itself, and with the chapter we'll post the chapter webinars upcoming also. So keep safe, and thanks very much to all of you, and good evening, good night, good day.
Bye.
Bye. Thanks, Professor Martinez.